Hey, welcome to another physics video lesson. We're going to build a circuit represented by this diagram in order to verify Ohm's law. So the R1 you see in the circuit diagram in our investigation will represent a variable resistor, and the one labeled R2 will be the device for which we want to show Ohm's law holds true. So in order to do this, we need to take measurements of voltage and current. So the diagram has two more items added to it. You can see an ammeter has been placed in series with the two resistors, and a voltmeter has been placed in parallel with resistor number 2, the one for which we're trying to verify Ohm's law. There's the actual equipment, and it's all connected. I'm going to take it apart and show you how I would reconnect it again to represent the circuit in this diagram. So we have our 2 meters. These are multimeters. Depending on how you turn them on, where you turn the dial, they can be set to act as either an ammeter or a voltmeter. We'll use two 1.5 volt batteries as a 3 volt source of potential difference. You see a little resistor with a few stripes on it. These resistors often have a color code that identifies their value in ohms. And then that other large box with a bunch of knobs on it represents the variable resistor in the form of something known as a decade box. So we'll keep the resistance constant. That fixed value resistor, the R2, will be 1,000 ohms in our first attempt, and then the variable resistor, R number 1, is going to be changed from 9,000 ohms to 4,000 to 2,000. We'll gradually reduce the value of R1. Now, by the way, if that's the case, if R1 becomes less and less, then the amount of overall resistance in the circuit becomes less, so the current in the ammeter should be greater, and according to Ohm's law, greater current through R2 should be greater voltage across R2. So that's what we expect to see, is both the voltage and the current shown in the last two columns grow as the values go down the data table, and they should grow in proportion to one another. There should be a linear relationship. We're going to repeat the exact same process, except use a 470 ohm resistor in case number 2. Okay, so let's dismantle this circuit and reconnect it. So take all the wires out. Just make sure we're explaining how we have these series and parallel connections. Okay, great. So let's just ignore the meters for a moment. Take the meter out of here, take this meter out of here. Let's connect a potential difference, a battery, with a resistor and a decade box. You notice the decade box has all these knobs that go from 0 up to 10, hence the term decade box. This knob controls the number of ohms in the 1 place. This knob controls the number of ohms in the tens place, hundreds place, and so on. So you can dial up any value of resistance you want. And so we're supposed to start with 9,000 ohms. So I go to the dial that controls the thousands place and set it to 9, and there I have 9,000 ohms. Okay, so with my decade box set to its first value, all I want to do is take a wire from the positive terminal of my battery into either one of the inputs on the decade box. It doesn't matter, there's no polarity to it. So I take another wire and continue on. I'll choose red for this wire because this is still going to the high potential side of the battery. Okay, now I need to connect it to my fixed value resistor, and I'll use one of these. We call these alligators, right? That's a banana, that's an alligator. Okay. So now let's take a black wire and go from the low potential side of our battery and then connect that to the other side of the resistor. So there it is. the circuit's complete. It's actually, well, it's almost complete. There is no flow of current because these batteries are not connected. This circuit is open at this point. So I need to go from the negative terminal of one battery to the positive of the other, and then this is essentially the switch in this circuit. So when I do make the connection, there's no way to tell the difference between having this circuit carry a current or not if I don't have anything to measure. So that's where the ammeter comes in, right? Now, we've got to dial it to the correct setting. And I don't expect to get full amps of electric current here. So I don't want to be on the setting that measures full amps. I expect to get milliamps, so I set it here. Now, depending on what setting you are, then there are labels down here to describe whether you want to go across those two inputs or those two inputs. It turns out this input is exclusively used when we're expecting to get large amps. This incorporates a fuse protection in the case where there's large current. So almost every setting requires inputs to these two. So anyway, there it is. It's set to milliamps. So an ammeter has very little internal resistance, right? There's nothing to protect this other than the fact that there's other resistance in this whole circuit. So if I break this open and I go through the circuit, now I just need one more wire. There we go. So right, I broke the circuit open and now I'm reconnecting it with the meter. It reads 0, but remember that's because I don't have my switch closed. Hopefully the values show up on the camera. Okay, so that's 0.3 milliamps. Now we expect as I reduce the resistance of the decade box, that's less overall resistance for the whole circuit. So the current goes up, and that means the current goes up everywhere. With more current in this resistor, then more voltage measured across it. So let's just see how much voltage there is across this resistor. A voltmeter is always connected in parallel with whatever device it's trying to measure the voltage of. And that's because voltage is a difference in electric potential. So a voltmeter, it doesn't require that we break the circuit open and then complete the circuit with the voltmeter. The voltmeter is its own path between 2 points. So I might want to put these clips on here. The electrons don't know what color the wires are, but you do, and so it's useful to try to match low potential to low potential. So if I take this wire and connect it to the low potential side of the fixed resistor, then I can connect the red wire to the high potential side, and now my voltmeter is in parallel with the resistor. Voltmeters have a really high internal resistance. So what I've done by making multiple paths now for electricity, current can get from point A to point B either through the resistor or through the meter. But because the meter has such a high resistance, very little current at this junction chooses the path to the voltmeter. Essentially, I have not changed the amount of current that flows through the resistor by introducing the voltmeter, okay? And I actually don't need these alligator clips because one nice feature of these banana wires is they can be piggybacked into other ones. So I can just insert that one to here and this one here. Okay, so once it's all connected, it just sort of looks like I don't know, a bunch of spaghetti laid out on the table, right? Unless you actually take your finger and trace the circuit, it's hard to recognize this is the same thing as this. Oh, and I haven't told this thing to be a voltmeter yet, so I just have to set it to the V. There we go. Now, careful, there's not 303 volts across this resistor. You always have to look at the units here. In this case, it tells us it's millivolts. So this is like an auto selecting meters, right? They'll tell you what range they're operating in, so make sure you read them carefully. Okay, so 0.3 milliamps and 303.5 millivolts. So the next is to change it from 9,000 ohms in the decade box to only 4,000. So I dial this down, close my switch. Okay, so now the current has increased to 0.61 milliamps and the voltage to 0.606. And in this case, right, it's already changed from being hundreds of millivolts to now it's calling it tenths of a volt, 0.606 volt. No longer says millivolt. All right, then our next data point, I changed this to 2,000 ohms of resistance in the decade box. The voltage is now slightly more than 1 volt, 1.008, and the current is now just a little more than 1 milliamp, 1.02 milliamps. The next data point is 1,000 ohms in the decade box. Voltage is 1.507 volts, and the current 1.52 milliamps. Now that's interesting, huh? This voltage, 1.5 volts, is almost exactly half of the voltage from my battery pack. This is a 3-volt battery pack in total. The value of this fixed resistor is 1,000 ohms, and the decade box is set to 1,000 ohms. When the two resistors in series with each other have equal values, then it's acting as a voltage divider that splits the voltage of the battery in half. There are 1.5 volts across the fixed resistor. If I had another voltmeter connected to these inputs, and therefore in parallel with the decade box, it would also read about 1.5 volts. So the 1.5 volts here, combined with the 1.5 volts here, verifies what's known as Kirchhoff's loop rule that says 3 volts gained by the battery is lost step by step across the resistors in the circuit. Okay, carrying on, let me disconnect, because for a moment I have to turn this to 0, and I don't want there to be zero resistance in the decade box at any point. So I unplug it and then dial it in the hundreds place to 500. And then I can reconnect. Interesting. Let's think about this again. The resistance of the decade box is 500 ohms. The resistance of the fixed resistor is 1,000 ohms, and it has 2 volts across it. But there was 3 volts gained by the battery. So Kirchhoff's loop rule tells us there must be another 1 volt lost somewhere to account for the 3 volts gained from the battery. And of course, that other 1 volt is across the decade box. Does it make sense that it would be 1 volt here and 2 volts here if this has half as much resistance as this one, right? 500 ohms compared to 1,000 ohms is a 1-to-2 ratio, 1 volt to 2 volts, a 1-to-2 ratio. That's not a coincidence. Our current is 2.02 milliamps. Okay, so we've got just 2 more data points. Let's change it from 500 to 250. So we'll go down to 2 on the hundreds place and 50 in the tens place. Now, this is 2.422 volts and 2.44 milliamps. Is that a coincidence? No, not at all. This is 1,000 ohms. Ohm's law says V equals IR. So if I multiply 1,000 times 2.44 milli, the 1,000 and the milli cancel out, and so I should get so I expect this to be 2.44 volts instead of getting 2.422. Within reasonable error, Ohm's law seems to be verified. And then in the final case, 0 volts across the decade box. Well, then that means there should be no voltage here, all the voltage here. I'm expecting this to read something close to 3 volts, and therefore this to be something close to 3 milliamps. Let's see if that's the case. Surprise, surprise. 3.05 milliamps and 3.024 volts. So all I have to do is replace the 1,000 ohm resistor with a 470 ohm resistor. So I can just disconnect reconnected in here, and then I can run you through all the data points on this one. We'll save that for part 2 of this video lesson.